Students, in this, my final installment of my Special Topics Lecture 1 coverage review videos on a systematic review of chapters 4 through 5, I'm going to teach you guys about specific heat and heat capacity. Or at the very least, I'm going to review those topics that you should already totally remember from last semester. Yeah, right. Anyway, let's go ahead and get started. So, a substance's heat capacity is the amount of heat required to raise its temperature by 1 degree Celsius or 1 Kelvin. The higher the heat capacity, the more heat is required to change a substance's temperature. Now, generally speaking, the higher the heat capacity, the slower something also cools once it is heated. With that, I want you to think about your experience personally and answer these questions. For each of these following pairs, choose the substance that is likely to have the higher heat capacity. Water or a cookie sheet? Now think about that. Think about water and how long it takes to heat that up versus how long it takes to heat up a piece of metal, a metal pan that's a cookie sheet. Whichever one takes longer to heat up and consequently longer to cool down must have the higher heat capacity. From your own personal experience, which of these two is it? The next example is rebar or a potato. Now remember, rebar is once again a piece of metal and potato is starch. Think about heating up a piece of metal versus heating up a potato. Which one takes longer to heat up and therefore longer to cool down? Whichever one does has the higher heat capacity. I'm not going to answer this for you, but I invite you to think about that and see if you can figure it out on your own. Now let's apply that to specific heat. The heat capacity of 1 mole of a substance is called its molar heat capacity, or C sub m. The heat capacity of 1 gram of a substance is called its specific heat capacity, or just specific heat, C sub s. So once again, C sub m is its molar heat capacity, and C sub s is its granular heat capacity. We call it specific heat, but honestly it's the same. It's heat capacity per gram versus Cm is heat capacity per mole. It would actually be easier if they just called specific heat granular heat capacity or something like that. But anyway, they don't. It's specific heat. So here's the equation for C sub s. So specific heat is equal to the amount of heat transferred divided by the grams of substance times the temperature change. Please keep that equation in your head as we go on. For example, it takes 209 joules to increase the temperature of 50 grams of water by 1 Kelvin. So water's specific heat capacity is once again the amount of energy up here in the numerator divided by the weight or mass in grams of the substance multiplied by the change in temperature. You throw that into your calculator, you discover that its specific heat is 4.18 joules per gram Kelvin, or 4.1 joules per geek. Yeah. And by the way, Kelvin and degrees Celsius here are interchangeable, and the reason is because you're only talking about the magnitude of a temperature change instead of the absolute value of a temperature change. And remember, each individual Kelvin is the same size as an individual degree Celsius, so you can interchange them right there at that point. Here's a table that shows very specific heats for some substances at this temperature. And yes, the specific heats do change if you change the temperature. All right, let's take a look at a problem. The specific heat of octane, whose formula is this, is 2.22 joules per geek. How many joules of heat are needed to raise the temperature of 80 grams of octane from 10 to 25 degrees Celsius? And separately, which will require more heat? Increasing the temp of 1 mole of octane by a certain amount, or increasing the temperature of 1 mole of water by the same amount? Now, I'm not going to do this for you, but invite you to attempt to do it on your own. And then if you wish, you can click the link here to a separate video in which I'll show you how to do it on the .cam or on the board. Let's take a look then at another one. The specific heat capacity of lead is this number. How much heat in joules is required to raise the temperature of 15 grams of lead from 22C to 37C? Now, I'm not going to do this for you, but invite you to remember that we're going to use the equation for specific heat that I just showed you. In this particular case, the one thing that is not known is the numerator in joules on top. So you can throw in all of the other numbers into that equation and then solve for joules, and it should give you the answer. And then this one. The specific heat capacity of liquid water is this number. How many joules of heat are needed to raise the temperature of 5 grams of water from 25.1 to 65.3 degrees Celsius? Once again, it's totally the exact same approach. We have all of the stuff that we need except for delta T here. We can determine delta T by just the difference between these two numbers and then throw them into that equation for specific heat and solve for the thing that we're missing, which is the numerator, the number of joules required in this instance. That takes us to the end of this exciting video lecture and the end of this coverage from Special Topics number 1. Whew. It's been a lot of coverage, but I hope you're excited about it. And I hope you're enthused about our upcoming coverage from Special Topics number 2, in which I will begin by doing a systematic review of Chapter 6 through, like, infinity or something. So until next time then, my wonderful students, I order you to have an enjoyable rest of your day.